You know, that has to be in context or it loses a lot of meaning. Alright.
It's like sentencing.
So, the square root function we just talked about is the inverse of a quadratic. Now, the quadratic function actually has both sides. Okay? But when I took the square root, I just left the positive. So what I'd have to do is define it like this. And does that look like it's symmetric across the y equals x line?
Yes.
Isn't that a fabulous straight line? And you squint and you turn your head to the right. Yeah, now it looks straight. Okay, so the first thing we're going to do is talk about how to graph these. The beautiful thing about learning how to graph functions using transformations is they all work the same way. The first thing we do is we shift our starting point. We could call this a vertex. We could also call it a starting point. And that shifting of that point happens the same way every time. It's the opposite of what's grouped with our x is our left or right. What's added to the end of the function is our y. So this is the parent graph. This one lives right here at the origin. This is y equals the square root of x, so it's not moving anywhere. And then how do we get the shape of this graph? We have to apply our moves, but what kind of moves do we do for square root function? They're numbers that we can take the square root of. Like what?
4.
4, I like it. Square root of 4 is 2. Let's pick another perfect square.
16. I was thinking cube, leave me alone.
Alright. What comes before 4? 1. What comes between 4 and 16? 9. I love it. Okay, so we go from the starting point over 1 up 1, over 1, 2, 3, 4, up 2, and that's how we would graph it. Now, generally, these last two are not going to fit. Usually, you just get a couple points, like the starting point and the first two moves. Now, we do have a restricted domain and a restricted range because we can't have a negative under the radical. Gives us imaginary. So the domain for the parent graph goes from 0 to infinity, and the range is also from 0 to infinity. Now, this entire function is increasing. So it increases over the entire domain of the function because it's going up forever. Every day.
What's up, bruh? Do you
For those of you that are watching the video, Millie has come to visit, and she always causes a disruption. All right.
She's been there for about 3
Let's
minutes.
go now.
Number 1.
She's not.
Naked and afraid.
Number 1 is.
You never seen, I watched the series. It's actually really good because
Number 1, where do we start? Where is the shift? The starting point shifted
up
to?
1.
3.
Up 1, but also
3 left.
left 3. Left 3, up 1. Left 3, up 1, starting point shifts. Okay, the 3 is grouped with the x under the radical. Those are grouped together, so we have to do the opposite. So that starting point shifts to -3, 1. Okay, there are no other transformations on this graph other than that shift. So I'm going to go pick those numbers I can take square roots of. The square root of 1 is 1. So I go right 1 up 1. The square root of 4 is 2. So I go right 4 up 2. The square root of 9 is, oh hey, it fits on the graph. 3.
Barely.
Just barely. And then I can talk about the domain. You can see from the graph the domain of this function starts at -3 and it continues forever right. The range, all the possible y values of the function. The lowest y value is +1 and it goes up forever. Now we could find a y-intercept on this one, but can we find an x-intercept?
No.
No, there's not one. The y-intercept, the easiest way to find the y-intercept is plug in 0 for x, it goes away. So the y-intercept is this weird number, 1 plus √3. Irrational. This entire function is increasing, and so it increases over the entire domain. So from -3 to infinity.
Will you ask us for all those?
Yeah, and on the back of your worksheet it talks about end behavior. I don't generally do end behavior with a square root because we only have one end that continues. This end comes to a stopping point, so you would have to say, as the function approaches -3 from the right, which we're not there yet. That kind of leads us into limits of a function, which kind of leads us into calculus.
And we're not there
And we're not there yet, so we're not really going to do end behavior on the square root function. Yes, Jack?
With the y-intercept, do you just get those two numbers from the original?
You sure do. You plug in 0 right here for x, because the x value on the y-axis is always 0. And so basically that makes this part go away. So you're left with the square root of 3 plus 1. So I just wrote a 1 plus the square root of 3. The real part, the rational part first, irrational second. Okay, on this one, there's nothing in their group with our x, so there's no shift left or right. There's a 4 at the end, so we're going up 4. Now, this has a -2 out in front, so these y values get multiplied by -2. That's going to cause a reflection, so it's going to go down, and it's going to be stretched. So instead of over 1 up 1, we're going to go over 1 and down 2. Instead of over 4 up 2, we're going to go over 4 and down 4. And that's all that'll fit on the graph. All right, the domain of this one, 0 is my smallest possible x value, so it goes from 0 to infinity. And the range, least to greatest, this goes down forever, so the least value is -infinity. My babies. Okay, I can't blame that on the movie. I'm struggling to draw infinity today. And the highest y value is 4. Alright, this entire function is decreasing from left to right. So it would decrease from 0 to infinity. And the y-intercept is obvious, 0, 4. We started with that. All right, number 3. This has one of those reflections that we're not used to. It's a reflection over the y-axis because there's a negative inside with the x. Whenever x has a coefficient, whether it's -1, as it is in this case, or if it's 2, as it is here, before we can figure out our transformations, that coefficient must be factored out. Otherwise, we'll get our shifts wrong. So if x ever has a coefficient, it must be factored out so you can understand what type of shift is occurring with your function. Now, this is really, like when we start graphing trig functions, that's when that makes the most sense. Right now, it's just something that you'll be like, okay, I'll do it. All right, so the starting point is at +2, -1. It's right here. But because there's a negative with the x, this is going to change all the x's to the opposite. So instead of opening right, this one's going to go left. And that's all I can fit. Alright, so number 4 is all messed up. We've got a reflection out here. We've got a vertical stretch. We've got a coefficient causing something to happen to it horizontally. So let's factor that out and see if we can figure out what's going on with that. If we take that 2 out, it leaves me with x minus 2 and a plus 5. So this one has that starting point at +2, +5. 2, 5. So because that x had a coefficient, we have to factor that out to determine the starting point. Now, this is weird. It's got a negative outside, so it caused that reflection over the x-axis going down. And these y's get tripled.
And then you gotta switch the y's.
Okay, And then we also have something going on with those x's. Okay? So, whenever something happens to the x is grouped with it, we have to do the opposite. The opposite of the -2 was +2. The opposite of multiplying by 2 would be dividing by 2. So all of these get divided by 2 or multiplied by 1/2. You can think of it either way. So we really go right 1/2 down 3. Weird. Right 2 down 6. Still odd. That's good enough.
Are you sure?
I'm sure. I'm happy with that.
Go right 3 down.
What you laughing at, huh?
You.
But
Ha 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 ha. Go ahead.
You guys, that's bullshit.
Hey, this one we have no y-intercept, right?
Really?
And I could also tell algebraically, because if I put in a 0 right here, I get the square root of -4, which is imaginary. That tells me the graph has no y-intercept.
yeah, that's a candy.
You actually can find the x-intercept. We plugged in 0 for y.
You get that?
Algebraically, it's a little ugly, but we can find it.
It's probably like 1, 2, 3. That's probably 3.
Yeah, you're right. Okay, questions? As I peruse the room, it appears that some of us are beginning to crash and burn.
Hey, anybody up?
Yeah, we're tired.
Feeling pretty good.
I have to stay here until 5.
I'm so tired.
I have to take a test. And I really want to go home. I might just not go.
I'm like, shut
Want me to start?
I'm done.
Well, I mean, usually I will take the L because I plan to
I can see it.
Alright, the next one. Cubed root. The next one is the cubed root. Now, like its inverse would be the cubic. We talked about that a minute ago. So the inverse looks like this, y = x cubed. So if I graphed it, it would go like this. And if I did a good job, then you could tell it is reflective across the y = x line. See that? That's closer. All right.
That's pretty straight.
Okay, so the neatest thing about learning to graph using transformations is the function, it all works the same way. You just have to look at the function and it tells you what your x's need to be. So for cubed root, our x's need to be numbers that we can take the cubed root of. Okay, great. 8. 1. Now the cool thing about this is we can also do negatives. You can take an odd root of a negative. An even root of a negative is imaginary. So this would be 2, 1, -1, -2. Now, the other nice thing about this is if we get rid of the extra and we look at just the function, it has no restrictions. It goes forever left and right. It goes forever up and down. And there's not much I can do to restrict it. So yay! For every cubed root, that's your domain and range.
There's a duck on my lake that just quacked. I'm not kidding. It's so sad. It tries. It sounds like a cough. I'm not even 100% serious.
All right. Number 1.
No, it tries to, but it can't.
All right, I feel like I'm losing the battle. But here we go. We're going to finish the last 4 so you can have class time to work on your homework and get it done. All right, so this starting point is right here. This starting point occurs at the inflection, just like it did for the cubic. So that's where our starting point is, right here. This is what we're shifting. So this one's going to shift it over 2, up 1. Then the cube root of positive 1 is 1. The cube root of positive 8 is off the charts. The cube root of negative 1 is negative 1. The cube root of negative 8 is negative 2. So I graph what will fit, and I don't worry about the rest. And then I just kind of make it swishy. For some reason, I had an extra swishy.
Swishy?
I shall name him Swishy, and he shall be mine. You were? Do you know about that?
That's what I just said.
Okay. It's squishy, but it's squishy. It's you know, Finding Nemo? The movie? Yeah, remember that little...
You're gone, Julian.
Remember the little...
Jellyfish.
Jellyfish.
What's going on right now?
She said, I shall call him Squishy and he shall be mine. And I was thinking like this. No, you think of songs, I think like...
There you go. Yeah, yeah.
Julian, you're lost. You're trying to fit funny ways.
Okay, so 0, negative 3 is where our next one starts, but we have the 2, which is going to take and multiply all of our y's by 2. Not many of them fit though, so we'll take the ones that do, and then we'll pretend about the rest. Now, this entire function is increasing. Like if I put my finger right here and I went all the way to the end, it would increase. This one's increasing. They're not always increasing. This one right here is going to decrease. I know it's going to decrease because it has that negative out in front, but so far they've been increasing. All right, where do you think the inflection point shifts on this one?
Down, left, forward. I mean, up. No, right.
Down,
Left,
left.
Left 4 is correct.
Forward.
All right, now we have a half out in front, so it multiplies by half instead of 2. So if I went over 8, I'd go up 1. Whoops, that's 9. Try again. If I went over 1, I'd go up a half. And then a half right there, and that's all that'll fit. Whee!
I was about to say, I thought I was doing it wrong, bro. It's just really small.
No, I won't grade it. No.
I need to like do the points and like highlight so you can definitely see that I got some points there, even though the line may not fall.
Okay, and then this one's going to start off at negative 1, positive 2, but there's a negative out in front, so it changes all those to the opposite. So we go left 1 and up, right 1 and down. And that's all that'll fit. So this entire function is decreasing from left to right. That's a decreasing function. Now on these, we actually can talk about the end behavior. I'll pick one, number 2. As x approaches negative infinity, and as x approaches positive infinity. Let's talk about what this function is doing. What are the y's doing? As we go this way, the y's are going down. So the y's are approaching negative infinity. As we go to the right, what are the y's doing?
Going to infinity.
They're going up to positive infinity.
And
Big
beyond.
B. All right, and that's it.
Oh, yeah.
So you have the rest of class. Oh, that's 25
That's
minutes.
a lot of time.
You can fit
That's
all
not-
Okay,
that's
so
not big for us.
that is, you don't have homework, you have classwork. Okay, you
I
have
need homework.
classwork.
Because if I don't have homework, I mean, I can't do anything at home.
Yeah, this
No.
is actually good for you because
I
I already
practiced
have
tonight.
so much stuff to do.
You're putting
So do it right now.
Yeah, I'm not
I'm
trying
trying
to.
but I want to be late for practice. But like, coach, what's doing homework? Okay, school.
Did I actually say that? My professor said that.